It's a warm summer day. All right, so in the world of good news, let's see, the weather's great. Okay, we need to take the hoods off unless you are like joining some religious group that requires you, young Jedi, to have your hood on. Okay, let's see. All right, so in the world of good news, let's see, 6 days until Adoption Day. Which means I won't be here next Wednesday, so maybe that's worth clapping about. Those days are rare. 13 days until move-in day.
Whoa,
Very exciting. But better than possibly both of those two things put together, Star Wars, 8 more days, and I have my tickets. Good.
Already?
Of course I do. I want good seats. Alright, so things that you need to know. Test corrections for Unit 4 are due tomorrow. They are due tomorrow. I'm available both today during lunch for support and tomorrow during lunch for support. Everyone's going to get this taken care of. If your name was in yellow or red yesterday, the students I'm concerned about, you're going to stop by today during lunch so that we can talk and make sure we understand where you are, where I am, and we'll talk about these videos. BC, that doesn't apply to you guys. Mario, that doesn't apply to you guys. Oh, homework, that does apply to you all. It's assignment number 70.
Is it easy?
Yeah, I did a really good job with that. Okay. And we are in a world where everyone is doing all of the homework assignments. Oh, do I have? Yeah, that's good. Good. We're in a world where everyone's doing all the homework assignments because we need to get our grades out of the toilet. All right. So, Jackie, can you make sure that we can see over here? I get 2, I get 5, I get 8, I get 12, I get 14, I get 16. Who's missing? No. Okay, and of course I've been back, you know. All right, so more good news. We are in the unit where normally students do really well. Grades go up, they bring their calculators with them to class every single day. They know what we're talking about. I've got some new calculator skills coming your way. Can I get a volunteer to read that notation? What is this new notation? How do you read it is the question. Check your notes if you need to. Jose, how do you read it?
The definite integral of f of x with respect of x from x equals a to x equals b.
Love it. Said it like a boss. Definite integral of f of x with respect to x from x equals a to x equals b. Ashley, before you die of being way too cold, how would you read that again? You just heard him say it, and then I said it again. So this is the point where you just repeat what we've just said. Ashley.
The definite integral.
Ashley, can you come on?
The definite integral of f of x with respect to x from x equals a to x equals b.
Excellent. Last one. Eric, how do you read this again?
The definite integral of f of x with respect to x from x equals a to x equals b.
Excellent. Now, what does it actually mean? We're all reading it correctly, but what the heck does it mean? What is the question being asked by this notation? Jesus, what's the question being asked by this notation?
How much area is bounded by?
How much area is bounded by 4 things? You have to identify all 4 pieces, Jose, Jesus. What are the 4 things? They're all here. They're all here in the notation. What are the 4 things? Name, help them out.
X equals A.
X equals A. The vertical line x equals A.
X equals B.
The vertical line x equals B.
The x-axis.
The x-axis, so like dx, the x-axis.
And the function.
And the function. 4 things. Jesus, what are the 4 things again?
X equals a.
The vertical line x equals A.
And also x equals b.
The vertical line x equals B. That's 2 of the 4. You get 2 more to go.
F of x.
The function, whatever the graph happens to look like. And the last thing?
The x-axis.
And the x-axis. Jackie, so what does this notation mean one more time? Yes, go for it.
Is it this way?
Oh my God, it's what he just said. It's what I just said. What does this mean?
Oh, the line. Wait. The graph is.
She's very cold. Her brain has started to
Is it
freeze.
the graph because of x, right?
Okay, there's a question. I read it. Everybody said it. It starts off with how much area is bounded by, and then there's 4 things.
Oh, the graph is f of x.
The graph
the x-axis.
The x-axis.
The line x equals a.
The line x equals a,
b.
and the line x equals b. Wow, okay, you guys are making me work for my money today, but that's okay, because move-in day is in 13 days. All right, so you might have some visual, like that's what I'm looking for. Definite integrals right now just mean area, and everybody's okay. Everybody's good? Everybody's good? All right, so show me that you're okay. Show me that you still have these skills. On your calculator, please, find the integral from 0 to 4 of the square root of 64 minus x squared with respect to x. While you guys do that, I'm going to take attendance and switch over. And Abraham, I'm going to need you to drive the computer a lot today. I hope that's okay.
Sí.
You should get a decimal number.
30.6. That's what I yesterday she was like, read. I didn't even read. Did you see the green? Did you see this? The green already.
All right, Abraham, if you could assume the position, that would be great. All right. Kevin, what'd you get for your numerical value here? 30.6. 1. Wait, 30 point? 6.116 or 30.612? Just quick thumbs up. How many guys are getting 30.612? Right, this needs to be that you don't even have to think about it. Your calculator does all of the work. But coming back to Ashley on this one, this 30.6116 means what? It means what? Still? It's an area thing. This 30.616 is how much area is connected back to the definite integral here. It's how much area is bounded by what four things?
X equals a, x equals
Well,
b.
connected back to this.
Oh, x equals 0.
The vertical line x equals 0. The vertical line x equals 4.
Square root of 64.
The graph of square root of 64 minus x squared, whatever the heck that looks like, and the x-axis. Everybody good?
Yeah.
We got this under control. I'm going to keep coming back to you. You're going to figure this out. The brain's going to thaw. Okay, good. So with all of that said, all right, Abraham. There we go. All right, you guys don't really need to take any notes. You just need to do a little bit of thinking. Kevin, if you could turn off the front light, please. Uh-oh. Oh, bummer. My bad. I had you guys connected to the wrong thing.
Yeah.
Okay. My bad. All right.
When I said this, you did this, I did this. But they claimed it was
Epic fail, DeRozier. Epic fail. Okie dokie. So, Geometers Sketchpad, one of my favorite things. Pedro, Kevin, stay with me. Okay, what you see here is the graph of square root of 64 minus x squared, what you guys just did on the calculator. The shaded region represents the region from 0 to 4. Now, you might be a little panicked right now because according to Geometers Sketchpad, the integral from 0 to 4 is 30.057. And according to our calculator, it's 30.611. Clearly different. Now, here's the thing. You may not even be able to see it. Because of Geometers Sketchpad, there's only so precise I can get it. I'm not actually starting at 0. I'm not starting at 4. I'm starting close to 0 and close to 4. That's why our number's off a little bit. But think about it. If I could get B all the way over to 4 and all the way over to 0, I'm not off by that much. I hope we're okay. So George Riemann died a long time ago. Is really the guy that pioneered this field. What he wanted to do is he wanted to know the area of this region. He wanted to come up with the value of the definite integral from 0 to 4 of this particular curve. Anybody see any challenges with this? What's tough with this compared to maybe what we did on Monday? Jackie, what do you say?
Like, it's like you can kind of see like a rectangle, but you have the edge that's not straight.
Okay, you've got the edge, like the curvy part,
Yeah.
right? Like, can you find the exact area of this particular region
No.
based on the tools that we have right now? No. If you think back to the graph we looked at on Monday, everything was like nice straight edges or curves. And we used our knowledge of triangles, trapezoids, rectangles. Everybody was okay? Coming up with this exact area is going to be trickier, so we need some ideas. What if instead of coming up with the exact area, you just wanted to estimate the area? Any thoughts on how we could estimate this? What do you think?
Like breaking down.
Break it down, like a dancer? What do you mean?
Like you can do like a rectangle.
Okay.
And then a triangle.
Oh, so you see like a rectangle and a triangle?
Yeah.
Excellent. Okay, Abraham, I want you to click over here where it says n equals 4. Double click, make it n equals 1. Double click n equals 1. Okay. And click show left rectangle. Everybody okay? We got one rectangle. How do we feel about that area? The area of the rectangle and how it connects to the area of the region that I want. Is this a good estimate?
Wait,
Pretty good estimate?
Yeah.
Is the area bigger than it should be or less than it should be?
Bigger.
Bigger than it should be. Roberto, why bigger? Jackie, I see you. Roberto, why bigger?
It's not in the outline of this semicircle, half circle.
Okay, you could also say like you've got this piece up here that you're not really wanting to capture the area for. Your idea then was to like subtract that off. But even with that, we're going to run into a problem because the piece that I don't want isn't a shape that you know. It's not a triangle, it's not a rectangle, it's not a trapezoid. Everybody okay? Jackie?
Okay, so when you did that,
Yep.
doesn't when you like put a point on any circle, you have like I don't know if is it a tangent line or like?
Oh my God, you're like on fire today. Well, except you're frozen. Okay. So this line segment, if you think about the top of the rectangle, is a tangent because it touches the curve just once. That's true. Everybody okay with the idea of like, let's use a rectangle to estimate the area?
Yeah.
And in this case, overestimate or underestimate? Overestimate. Now you might look at this and you might say, well look, if the true area is 30.057 and my estimate is 31.390, that's not too bad, is it? I want to get it better. Any ideas for how to get a better estimate? Use your geometry skills. What could you do? One rectangle gives you a pretty good estimate. Any thoughts on getting a better estimate? Abraham, click on this, make it n equals 2. Well, look at what happens with two rectangles. If you get two rectangles, now you're covering that same distance. You're going from 0 to 4, but I'm going to use two different rectangles. Overestimate or underestimate?
Over.
Still over? How does that estimate compare to what we had before?
It takes away
It's getting a little bit better?
Yeah.
So any ideas for making this better still?
Make
more
it very
parts.
rectangle.
More rectangles, right? How many more?
2,
4? Okay, make it 4.
Isn't it the higher the number, the better?
yeah.
Okay, n equals 4. Now I've got 4 rectangles. The estimate was 30.8 something, now it's 30.52. I heard somebody just say, isn't it going to be true that the greater the number of rectangles, the better the estimate?
Yeah.
Yeah.
Okay, let's check it out.
10.
Click on, okay, 10. 10. Now we're at 30.255. There's still error. There's still all these little pieces. Everybody good?
Yeah.
Yeah.
Okay, so the more rectangles, the better the estimate is? Okay, click on n plus 10 nonstop. This is going to increase the number of rectangles 10 at a time. So 10 rectangles, 20, 30, 40, 50, 60, 70. The rectangles, there's so many, they're so skinny. Just like me, skinny but tall. I swear if you laugh, you fail. Okay, they are so skinny, they're so narrow. The skinny, oh, we've looped back around. But as the rectangles get skinnier, I need more rectangles, but the estimate gets better.
Yeah.
Are we good?
Yeah.
All right, so that is one method. This is going to be called the left endpoint method. Click on n plus 10 nonstop. Go back to n equals 4. You really figured this out. N equals 4. Click OK. We're going to call this the left endpoint method. The reason that we call it the left endpoint method, look at all 4 rectangles. The way you determine the height of each rectangle, you look on the subinterval and you use the left end to go up to the curve, determine how tall the rectangle is, and come back down. Are we good? Yes. This is one of 4 different methods that you need to know. Left endpoint method. Any guesses about another method? The right endpoint method? Okay, click hide left rectangles, click show right rectangles. Okay, right endpoint method. You're covering the same distance, but now with 4 rectangles. When you make a rectangle, though, if you look at all the rectangles, it's the right side of the rectangle that determines the height. Are we good? Exact area or an approximation? Hold on, Jackie. Exact or an approximation? Clearly an approximation. Overestimate or underestimate?
Underestimate.
Underestimate, Pedro. Why underestimate?
There's still a little space that isn't covered, but
You've still got some little space that I'm not capturing. And if I look, I can see the numerical values, 29.501 compared to 30.057. Underestimate. Jackie?
Okay, so can't you just like have the left sum, right? The left sum minus the right sum in order to get the parts that you're not getting? You know, like
Good ideas. That's not necessarily going to work, but keep thinking. Keep thinking. Okay, and if I want to get a better estimate?
You just keep
Better estimate?
decrease the number.
More rectangles, right? So let run it. N plus 10 nonstop. Right, and already we're seeing better and better and better approximations. Good, that's 2 of the methods. Okay, click N plus 10 nonstop. Go back to N equals 4. Here comes the third method. Third method is the midpoint method. Guess. What are we going to do with the midpoint method? You're going to determine the height of the rectangle using the middle. So let's do it. Show the midpoints. So we're going to hide right rectangles. Sorry. Hide right rectangles. Hide right rectangle. Okay, Abraham's broken. Hide right. Okay, good. Now show midpoint. Have a quick conversation with somebody near you. What's going on here? What's different with the midpoint method?
it's like the highest.
It kind of, it gives you the first, the height of the first one, and then if you just look like
on the outside, it's the same level.
it has like an overestimate.
So whatever the little piece from the outside, you can put it.
All right, Juan, let us in. What are you seeing here? What are you seeing with the midpoint method? Why might some people really like this midpoint method?
Because like the little piece that is on the outside, you can put it on the inside.
So you're focusing, I think it's easiest to see with this last rectangle. You've got this piece of the rectangle that is outside of what I want. So that's going to give me too much area. Keep going. What were you saying?
So you can add it to the little space that is in the inside.
You've got this little space over here that you missed. So in this case, you're getting too little area. Too little area over here, too much area over here. What's going to happen is they're not going to perfectly cancel out, but they're going to balance out maybe a little bit better. Are we good with that? Yeah. And if you look at your estimate, 30.080 using just 4 rectangles in the midpoint method, you're getting really close really quickly. We're good? Mm-hmm. And you want to get better? More rectangles. Last one, Abraham. Hide midpoint method. Show me the trapezoids. Check it out. What do we think about this trapezoid method? How good is the estimate?
It's pretty good.
It's pretty good. Like, it's, in fact, it's so good you can barely see whether you're missing area or whether you have too much area. You're looking at 30.057 is the approximation, is the actual value, 30.012 is the true value. We've never been so close so fast. We're good? Okay, 4 methods. What are they? Left endpoint method, right endpoint method, midpoint method, trapezoid method. We've got 4 different methods that we're going to use to approximate the area. Everybody good? All right, Abraham, why don't you come on back? for a little bit because Carlos misses you. And can I get somebody who can read with some passion, with some enthusiasm? I get a volunteer, I get a victim. Either way, it's going to be fun. Roberto, victim that you are. The name is George Friedrich Riemann.
George Friedrich.
Oh, and the good news is whenever you want to stop reading, just call on somebody else.
George Friedrich Riemann developed a technique for determining the exact area bounded by a function f of x on the x-axis over an interval a, b.
Yep.
Today we are going to continue down the same road that he traveled over 150 years ago. His idea was simple enough to estimate the area bounded between the function and the x-axis over an interval, divide the interval into smaller sections called partitions, then create known geometric shapes to estimate the area of these smaller intervals, and then find the sum of the areas.
To get a more accurate answer?
To get a more accurate answer, make the sub-interval smaller, then smaller, then smaller, then smaller, then smaller, then smaller. Evelyn?
How small is that last word? Infinite?
The word is infinitesimally.
Infinitesimally small.
Teeny, 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 tiny.
As the length of the sub-intervals becomes smaller, the number of intervals must become larger and larger and larger and larger. How large is that last one? Infinitely large. Your final results will be the exact value of the definite interval. Wow, if this wasn't impressive enough, he did all of this without a graphic calculator.
Yes, it was 1826 to 1866. There was no graphing calculator. There was no Geometers Sketchpad. There was just brilliant mathematicians doing this work. Now, sad news, this unit, all the work we're going to do with the definite integral is with the graphing calculator. Sad news. The good news is that in the unit that we tackle after we come back from winter break, we do all of this without the graphing calculator, which is really where the excitement and the calculus kicks in. So you might understand now why this is the unit where grades go up. You're going to do a lot of this on the graphing calculator. All right, Kevin, can I get you to turn the lights on? All right, here we go, friends. First one ever. On... Oh, I can't see anymore. Okay, on your calculator, please. I need you. Show me that you can actually pull off the calculations here. The integral from 0 to 6, 4x squared e to the negative x plus 2. Integrate that with respect to x. I'm going to show you two ways that we can do this. Actually, I think I just lied. Sorry, I didn't mean to lie. Friends don't lie. Find the value.
Oh my God.
Just make sure everybody's got these seals. You want to go on the calculate screen. Remember, it's menu, calculus, numerical integral. You type it all in. You get some beautiful number. Juan, what did Roberto get in his calculator?
19.5042.
19.5042 is what I heard?
Yeah.
Is everybody else getting that? Typing this into the calculator, super easy, right? Okay, that's the exact value. I want to do this lesson in a slightly different order, which is why we're filming again. I'd like for everybody to go down to method number 4, the left endpoint method. Okay. We know 19.504 is the true answer if I wanted to find the integral from 0 to 6. What I want to do is I want to estimate the value of the integral from 2 to 6. First of all, without knowing anything, without doing the calculations, should the answer to the definite integral from 2 to 6, 4x squared e to the negative x plus 2, be larger or smaller than this one?
Smaller.
And if so, why?
Because it's taken out from 0 to 2.
You're taking out
The area.
This guy said find the area underneath this function in the x-axis from 0 to 6. This guy says just go from 2 to 6. Are we okay? We're covering less area, so this has to be smaller. Okay, on your calculator, go find the number. We know that this one's going to be smaller. We don't know how much smaller. Use your calculator, show off. What are we getting? 12.9. I need 2 more decimal places. 12.918. 177, which would round to 12.918. As long as we're accurate to 3 places after the decimal, we're good. All the friends are good? Okay, now we're going to do what Riemann did. I want to estimate the value of this integral, and you've got to pay attention to the method. We're going to do this using 5 rectangles of equal width and the left endpoint method. So here are the important things. 5 rectangles and the left endpoint method. Feel free to use the markers if you need them. Here's x equals 2. Here's x equals 6. I want to come up with my approximation. I want to come up with a marker too for that area. Pay attention to the method. We're supposed to use the left endpoint method and 5 rectangles of equal width. So my first question for you all, if you're going to go from x equals 2 to x equals 6, and you're going to partition, you're going to chop up, Jackie, I think, can you turn the camera maybe a little bit? You want to chop up this interval from 2 to 6 with 5 rectangles of equal width. How wide is each rectangle going to be? You need to go all the way from x equals 2 to x equals 6, and you need 5 rectangles.
1.
If you go with 1, too much.
It's like 2.
You need to go from x equals 2 to x equals 6. How long is that distance?
Wait, what?
3?
Not like to break it up.
No, not 3. 5 rectangles. You have to use 5.
4 divided by 5.
Okay, where's 4 divided by 5 coming from? Why 4?
Because the distance is 4 and there's 5
The
rectangles.
distance is 4, and I want to chop this up into 5 equal rectangles?
So it's 0.8.
Okay, so 0.8. The calculations, I'm going to write it this way. Delta x equals b minus a divided by n. The delta x is going to be the width. The b, why would I use b? That's like the top limit, or it's the right endpoint. The significance of the a is your left endpoint. And the n is the number of rectangles. So what Ashley did, nice job Ashley, you said 6 minus 2 divided by 5, and you get 0.8. 0.8 is how wide each rectangle is going to be. Well, let's do it. My first rectangle has a width of 0.8. It starts at 2. Where does it end?
2.8.
It should end over here at 2.8. The next rectangle starts at 2.8. Where does it end?
3.6.
3.6.
Sorry.
The next one starts at 3.6. Where does it end?
4.2.
Uh-oh.
Oh.
4.4. Next one starts at 4.4. Where does it end?
5.2.
5.2. Last one starts at 5.2. Where does it end?
6.
6. Do we have the right width?
Yes.
Clearly, we went all the way from 2 to 6. 5 rectangles of equal width. Now we've got to be careful. What shape are we using? What method? Not L'Hopital's. Ah! What method? What method? Go back to the problem. There's 4 methods we could be using. Left. The left endpoint method says for each partition, how do I determine the height of the rectangle? I use the point on the left. I go up to the curve, I go over, and I come back down. There's the first rectangle. For the second rectangle, which side do I use? Still the left. So go up to the curve, come over, come down. Third rectangle, go up to the curve, over, down. Fourth one, up, over, down. Fifth one, up, over, down. Okay. And don't get all OCD with the ruler. I mean, it's just a sketch. Overestimate or underestimate? Look at those rectangles. What has to be true? Underestimate? Overestimate?
Yeah.
This should be an overestimate. This should be overestimate. Each of these rectangles captures more area than what you want, so I'm expecting an overestimate. Okay, let's grow your skills. So this integral from 2 to 6 of the function I'm going to call f of x is going to be equal to that area? Exactly equal to the area? If I find these 5 areas and add them up, the definite integral is exactly equal to? It should be approximate. It'll be close. I'm going to write A1, A2, A3, A4, and A5 to represent the area for each of the 5 rectangles. Okay, let's do it. The area for a rectangle, you guys know the area for a rectangle. Length times width or base times height. So let's talk about that first rectangle. Length of the base. How long is the base?
0.8.
It should be 0.8. We're going from x equals 2 to x equals 2.8. So it has a base length of 0.8. Now what's the height?
It's from the top part from
The height is determined by the left endpoint. So how tall is that? Now, some of you guys are going to say 4, and I kind of set you up to give me the wrong answer here. What I think you're saying is 4 because it looks like 4. But it could be 4 point something, it could be 3.9 something. I want to get the exact value here. The way you get the exact value is by plugging x equals 2 into the function. The coordinates here are the point 2 comma f of 2. I'm going to take 0.8 times f of 2. In fact, for reasons that will be obvious in a little bit, I want to rewrite this over here. 0.8 is the base, f of 2 is the height. That gets me the first rectangle. Second rectangle. What's the base, what's the height?
0.8.
0.8 is the base, right?
Times 2.8.
Times. When I look at the second rectangle, how did I determine the height? We use the left endpoint, which is 2.8, and you plug it into the function. I think we're okay with that? Okay, that's the second rectangle. All right, third rectangle. Jesus, coming your way. Give me the area for the third rectangle. What's the base, what's the height? The base has a length of 0.8. What's the height? It should be f of 3.6. I completely agree. Okay, fourth one. Evelyn, what's the base, what's the height?
The base is 0.8
The base is 0.8.
and the height is 4.4.
The f, not 4.4, but f of 4.4. And Beto, close it off for me. Base and height.
The base is 0.8
Base is 0.8.
and the height is f of 6.
It's f of 6?
5.2.
F of 5.2. Remember, because you're using the left endpoint method? All the friends are good?
Yeah.
Okay, so good news. If this is a free response question, the setup is probably about 2 points. Jackie?
You don't do the 6?
You don't do the 6 because x6 is not being used to determine the height of a rectangle. You're using left endpoints only. All the friends are good? Okay, Abraham, you need to go back. And you guys need your calculator. And here's what you need to do. We need to plug all this into the calculator to come up with the answer. Now, what you need to do first, this is why I need to write it. Let's graph the function. Okay. Oh, good, you're already in there. Good. So graph the function. Zoom in if you need to, but you're going to graph the function.
4x squared times
Yeah, that's where
You do the S.
No, just the function. The 4x squared e to the negative x plus 2.
the same, like just
Oh,
one.
okay.
I guess and then you can put in your calculators.
F.
So 4x squared e to the negative x plus 2.
F of 2.
Okay. We've got the graph. The graph matches what we're looking at. Okay. Now what you need to do is calculate these values. And my charge to you is I want you to do this in one step. So we're going to leave the graph, go over to calculate. Go over to calculate. And this series of things, type it in. So you're going to type 0.8 times, now here's where you need to be careful. What you see on the board is f of 2. What do you type into the calculator?
F1 of 2.
f1 is the name of the function. Maybe you typed it in as f2 or f3, whatever you typed it in as. If it's f1 and you know you're doing it correctly if the f1 shows up in bold. It says like, oh, this is a function whose name I know. So f1 of 2 plus the next one. 0.8 times f1 of 2.8. And f1 shows up in bold. Yes, sir?
What if you didn't get that graph when you put it in?
Let me see it. Oh, it's just because
But it's
you've got the right graph. It's just a weird window. Right. You're going to get really fast at typing this in. So F1 of 4.4. Plus 0.8 times F1 of 5.2. What'd you get?
13.6290.
13.6290. Let's see what Abraham gets.
You don't type that in. And then you go away.
13.629?
Yes.
How many guys are honestly getting 13.629? Okay, you didn't get that. So here's the good news for Delia and anybody else that didn't get that number. The majority of the work comes in the setup in the beginning. So you get 2 points for that. If you are running low on time, if you type it in incorrectly into the calculator and you don't get 13.629, you're going to lose 1 point, but that's it. Are all the friends okay?
Yes.
All right, now I want to push your thinking. So go with me back over to method number 1, which is the midpoint method. I want you to read through that problem. Abraham, you done. Thank you so much for the work that you've done. They are so ready for excellence now. Take a little bit, read through the problem, set it up, see what you can do. Find the value of that definite integral for partitions of equal width and the midpoint method. So you want to go from 0 to 6. For partitions of equal width, midpoint method.
So it's like, so you find the highest one and you like escalate.
You want to go from 0 to 6 using 4 rectangles of equal width. The first question you want to ask yourself is how wide will each rectangle be? Remember to figure out the width. we would do 6 minus 0 divided by 4, which should be 1.5. All the friends are okay with the 1.5? Okay, the 1.5 tells you how wide each rectangle is going to be. So I start at x equals 0. Where does this one end?
1.5.
At 1.5.
And 3.
The next one goes from 1.5 to 3. The next one from 3 to 4.5. And the last one goes from 4.5 to 6. I arrive at the place I need to. That's the partitioning. You've chopped it up. Now here's where we need to be careful. In last class, I came to this problem first. I shouldn't have done that. I blew their minds. What method?
You draw it from the inside and then
We're using the midpoint. So on this first rectangle, the way I'm going to determine the height is to use the midpoint. What's the midpoint between x equals 0 and 1.5? 0.75. The way you're supposed to do that is you like add these two together and divide by 2. So x equals 0.75 is important to us because it's the midpoint. What that means is that when I make my rectangle, I use this point, I go up to the curve, oh, that's how tall it is. How wide is it? The height is determined by the y value, but how wide? The full 1.5. So I'm going to go from x equals 0 to x equals 1.5, and I'm going to make my rectangle. That's the first one. Talk to me about that second rectangle. Where's the midpoint? Halfway between 1.5 and 3. 1.5 plus 3 divided by 2 is 2.25. Go up to the curve, and then you make your rectangle. That's your second rectangle. Midpoint for the third rectangle. Halfway between 3 and 4.5. Okay, Roberto, I'm going to freeze you for a little bit. We all know you know how to add two numbers and divide by 2. I'm so proud. Took you in off the streets, and you can add and divide. Okay, between 3 and 4.5, the midpoint is halfway between 3 and 4.5. Good ears. I took you in off the streets as well. And now you can copy off other smart people. Okay, x equals 3.75. Go up to the curve. Make your rectangle. Last one, midpoint. Halfway between 4.5 and 6 is 5.25. Okay, x equals 5.25. Go up to the curve, make your rectangle. 4 rectangles. So the integral from 0 to 6 of f of x dx is approximately what I get when I add the areas of those 4 rectangles together. These are rectangles. Area is relatively easy based on type. Evelyn, how are you feeling about that first rectangle? Okay, so let's do this one together. This first rectangle, how long is the base?
1.5.
1.5. How did we get the height? The height, we're using the midpoint method, so you go to the midpoint, the 0.75, and how do we get the height? You go up to the curve, you need the y value. So it's going to be 1.5 times f of 0.75. Yeah.
Can we use 2 methods at the same time?
I'm not going to normally ask you to do 2 methods at the same time. We're going to focus on just one method. There are some reasons why you'd want to combine 2 methods, but let's not worry about that today. Okay. Everybody good with the first one? No? The base is the 1.5. The height is whatever the y value is at the midpoint. All right, somebody else. I want to get some hands on this. Area for the second one.
1.5.
Or you could just call it out because who cares what I want. Okay, 1.5 times what's the height?
F of 2.25.
F of 2.25. The width, the base is 1.5. The height is whatever the y value is at 2.25. Okay, Kevin, talk to me about the third rectangle. Tell me about the base, tell me about the height.
Base is 1.5.
The base is 1.5. Should be 3.75. Okay, and Carlos, tell me about that fourth rectangle. What's the base, what's the height?
1.5
Plus 1.5
plus 1.5 f of 5.25.
times f of 5.25. And you're going to type it into the calculator, and the calculator is going to do all the work for you, and everything's good. And just to save ourselves a little bit of time here, 19.647 is what your area should be. And Naeem's got that? We doing mostly okay? Yes. All right, we get 7 minutes left. We're going to go a little fast on this one, but you guys are going to be fine. One more. Method number 2, trapezoids. You've totally got this one under control. Take a minute, read through this, mark it up, make sure you know what we're looking for.
It's 1 minus 6, right?
No, it's 6 minus 1.
Because A is B. So A, it's B minus A.
Okay, something's going wrong with your calculator, Jackie, because your F1 is not showing them as bold. It's still in italics. Delia.
No, it doesn't. F1, it does.
Oh, were you doing it over here? You want to be over here? Okay. Alright, she did a quick stroll through the room, which is a little bit of a lie, because I just stayed with Delia and called her Jackie.
It's 1.25, right?
Okay. We're going from 1.64 trapezoids of equal width. My question, first question, always first question. How wide's each trapezoid?
1.25.
Should be 1.25. So 6 minus 1 divided by 4. You say, how long is the interval? Divided by how many shapes of equal width do you need? There will come a time, we'll call that tomorrow, where they won't be equal width. Today they all have equal width. So next we go to the partition. You start at x equals 1. Where do you go to next? 2.25. The next one starts at 2.25. Where does that end?
3.5.
X equals 3.5. The next one goes from 3.5. Where does it end?
4.75.
4.75. The last one starts at 4.75 and it ends at 6. Hallelujah. Exactly the way it should be. Now, when you make trapezoids are different. To be a trapezoid, you have a pair of parallel sides. You guys all know that the area formula is 1/2 the sum of the bases times the height. The bases are the sides that are parallel to each other. That's the important thing. The height is the perpendicular distance between the two. How do we make trapezoids? If you think back to what we saw in the Geometers Sketchpad, you looked at these two sides here. They were connected, and that's your first trapezoid. Your second trapezoid starts here, ends here. Connect them. Starts here, ends here. Connect them. Starts here, ends here. Connect them. 4 trapezoids. The integral from 1 to 6 of f of x dx is going to be approximated by adding those 4 together. I know I'm going a little fast with this first part, but I think everybody's okay? Okay, so here's the question. How do I find the area for the first trapezoid? I want to get some hands on this, don't call it out. I see 1, I see 2, I see 3, I see 4. Carlos, tell me about the first trapezoid.
1.5.
1.5?
1.25.
Oh, slow down. I want to use this area formula.
Oh, 1/2.
So it's going to be 1/2 times what?
Times 3 plus
3. Where did 3 just come from?
the base on the top.
But I think you're saying 3 because it looks like 3? I don't want looks like, I want the exact value. Help them out.
F of 1.
You need to actually plug in x equals 1 into the function to get the exact y value. I know visually you're kind of doing that. You're like, oh, it'll be somewhere around 3. But f of 1 is the exact answer. 1/2 base 1 plus what's base 2?
F of 2.25.
F of 2.25. What's the height?
1.
This is the weird part.
Is it 4?
Because these are the bases. The bases are parallel. What's the height?
4?
The height is this guy here, because the height is the distance between them. So it's 1.25.
Wait, so is it always going to be 1.25?
For this problem, yes. Stay with me, Ashley. It's going to be okay. Okay, Ashley, second trapezoid. Me and you.
1/2
1/2. How long is the first base?
F 3.5.
Whoa, whoa, whoa. The second base. Second trapezoid.
2.25
F of 2.25
plus F of 3.5
plus F of 3.5. What's the height?
1.5.
Times
1.25.
1.25. Remember, they all have the same width. Okay, Pedro, coming your way. Tell me about the third trapezoid. 1/2. F of 3.5 4.75 and then times 1.25. And then the last one, 1/2 F of 4.75 plus F of 6 times 1.25, and I'll tell you the numerical value that you're going to get, 16.861. 16.861. 2 nights homework is a little bit of practice with all 4 methods. We did left endpoint, we did midpoint, we did trapezoid, we didn't do right endpoint, and I think that's the one that you should just keep finding.
Yeah.
Okay?
It's 16, right?
It's 16.861. Nice job today. Test corrections due tomorrow. If you're struggling, see me at lunch.